We just finished in the last chapter talking about electrical forces and electrical fields. And now that we've done that, we are ready to talk about electrical energy. In this video, we will talk about one of the measures of electrical potential energy, which is electric potential, also commonly known as voltage. So consider you have a parallel plate where the left side is positively charged and the right side is negatively charged, and you place a positive charge near the positive plate. Before you let go, you know that the positive charge is going to be repelled by the positive plate and attracted to the negative plate. In other words, this positive charge is going to follow along the electric field lines from positive to negative. Now, since you know that that's going to happen, that means that there is the potential of movement. Therefore, you have potential energy. Now, the electrostatic force, which we talked about in chapter 16, turns out to be a conservative force. And because of that, potential energy can actually be defined. Remember that potential energy is only something that comes from conservative forces. Now, any changes in electric potential energy would be the negative of any work done by electric force. So recall that work is defined as force times distance, but work is also equal to the negative change in potential energy, which is what we just said. Electric potential energy is negative of work done. And that helps us to define the work. Now, to define the force, we're using the electric force. That's just the charge Q that's inside of your electric field times the electric field itself. And that was also from a definition in chapter 16. So if we substitute those in, then we find that a change in potential energy from some final point B to some initial to minus some initial point A would equal negative QE, that's your electric force, times distance. Force times distance is work. And so here we've got a good definition for change in electric potential energy, negative QED. Now, just as we took the electric force and divided out the value of the charge itself that's in the electric field to define the electric field, we could do the same thing here. In this picture, we have some specific charge Q inside this field, and to know the change in potential energy, you have to know the charge. But if we take that potential energy and we divide out the charge, then there is a measure where we don't need to know what the charge is in the middle. It's irrelevant. And so this is the definition of electric potential. The potential energy per unit charge, also known as voltage. The unit of voltage or electric potential is the volt. And 1 volt, since voltage is potential energy per unit charge, 1 volt would then equal 1 joule per coulomb. Now, remember that when we first talked about potential energy has to be measured in reference to some other point. In other words, we can only measure changes in potential. If we were to talk about just VB, just one number, that wouldn't make sense. That'd be like saying I have a potential energy of 3 joules. Well, is that relative to the desk or to the floor? I don't know. So you have to have a change in potential from one point to another. That's the nature of potential energy. So whenever we talk about potential, it's always between 2 points. And so calculating that means that the change in potential would be change in potential energy divided by my charge Q, which would be negative work divided by my charge Q, which if I go back here, that makes sense. This is my work divided by my charge Q. So work divided by charge Q would equal negative ED. And so we've got ourselves another equation for voltage, and that would be that voltage is negative electric field times distance. So I brought this up earlier, but the analogy between gravitational and electrical potential energies is very close. Remember that potential energy for a falling object is calculated as mgh. If this is mass, then the potential energy here would just be mgh. But if I double the mass, then my potential energy would be double the mass times gh. Likewise here, if I have some charge q, potential energy is following this equation here. Potential energy would then be q times v. Q times v. This one would have a potential energy of qv, whereas this charge down here would have a potential energy of 2q times v. So just like with gravitational potential energy, where you double the mass, likewise, if your electric potential energy will double if you double the charge. So work, we already looked at this earlier. Work is negative Q times the change in potential, electric potential. And so that introduces a new unit of energy that we can use for the scale of electrons and atoms. This scale of energy is known as the electron volt, or EV. 1 electron volt is the energy gained by one electron, so the charge of one electron, through a potential difference of 1 volt. So work is equal to negative QV. Charge of one electron, remember, is 1.6022 times 10 to the negative 19th coulombs, times going through a potential difference of 1 volt, so we multiply that by 1 volt, and that gives us 1 electron volt is equal to 1.6022 times 10 to the minus 19th joules. And there's our new unit for energy on the subatomic scale. Now we can also solve for the electric field knowing a voltage. So if we know a voltage difference, so say we have a parallel plate. Oh, that's not very straight. Let's try that again. A little bit better. So if we have a parallel plate where there is an electric field between the two plates, and you know the voltage, VBA, then we can find the electric field, assuming we know the distance between the two. If we solve for the electric field, then we find that the electric field is going to be the negative voltage difference divided by the distance d. So in general, we can say that the electric field in a given direction at any point in space is equal to the rate at which the electric potential decreases divided by the distance in that direction.